So now I'm going to hand it off to Keith so he can talk about the volatility piece of the project.
Thank you, Andrea. Hi, Professor Hahn. So part of my responsibilities in this project was during part one of our final project, which was looking at the volatility of the 6 stocks that you provided for us over 2 years. So just to begin, this is how I approach this part of the project. I first started with reading the text files. This was probably the most challenging part that I had, just because I've never used any input-output file reading before in C++. And my main problem was putting it in the right format. And so when you download it from Yahoo, it gives you the file in a comma-separated format. And this does not work for C++, so you have to save it as tab-delimited text file. So I had to learn the hard way, and once I learned that, it was pretty much smooth sailing. I created my function, and it uses a file name as one of the parameters, and then it also uses the array size, because what it does in the function is it creates an array for the stock prices, and then it loads it from the file that it reads. And so what it returns is the array of stock prices. So here I have my function. This is a little snippet of one of my code. This is where I call my load stock function, which will read this text file and create an array of size n1, and it will return this array for the closing prices for Google. Okay, now the volatility equation. Pretty much what it uses as parameters is the closing prices, so the array, as well as the array size. And I use for loops for the summation, and then just basic algebra to finish the calculation and return volatility. And so this is pretty much from start to finish my volatility calculation. So I'm creating the array for Google, and then loading the stock. I have a little cout statement here, and then I call the calculate volatility function. So that was pretty much my approach. And I did this for each year and for each stock. Okay, and so these are my results. Let me move over here. So here I have a little table right here that basically sums it up. Year 1, year 2 with return and volatility. And I thought it would be interesting to see how volatility correlates with return. And well, first of all, what I see in terms of volatility is that year 2 was generally less volatile than year 1. You see that for almost each stock besides Apple, volatility decreased. And so here I have that right here. Year 2 is more volatile for Apple, and this is basically the reason why. It fell 31% in year 2, and then in year 1 it gained 81%, so that's quite a contrast. And it explains why the volatility jumped from 27% to 33% between 2 years. And just as a general trend that I found, which is not true in all cases, but in most, and that is that decreases in volatility are generally accompanied by positive returns. This can be seen if you compare things like just a standard market index and something like the VIX. So the VIX will always rise when the market falls. Well, not always, but generally. And the same is true for if the VIX falls, then the market will generally rise. Okay. The next part of our project, our final project, was the binomial model. So basically, what the binomial model is it's a lattice-based or a node-based model that uses future prices of the underlying stock to value the option today, pretty much. And one of the assumptions, the general assumption of the binomial model is that the underlying stock follows a random walk. So what does that mean? The random walk means that so the stock will have the ability to move up or move down based on some probability that has a specified distribution. And so that's something that we're going to see when we go over how the binomial model works. One good thing about the binomial model, and the reason why it's so vastly used in finance, is because not only can it price European style options, but it could also price American options. And the math is a lot simpler, so it's easier to understand. So the model was basically created and introduced in 1979 by Cox, Ross, and Rubenstein. And their implementation is generally used the most. And one of the assumptions that distinguishes this model to the Jarrow-Red model is that it assumes risk-neutral growth. So that means that for small increments, for small delta t's, your binomial model will behave as a risk-neutral asset or a risk-free asset. Next in line in terms of popularity is the Jarrow-Red model. The Jarrow-Red model is also known as the equal probability model, and that is because it assumes that there's an equal probability that the underlying asset will move up or down. So the name is pretty well. And this assumption removes the assumption that the binomial model acts like a risk-free asset. So let's take a look at the procedure. So there's basically 3 steps in this model. The first step is estimating the stock prices at future times. And once we're allowed to do that based on our probabilities and then our up factors and down factors, we will eventually end up at a stock price at the time of expiration. So that's going to be our first step. Our second step is going to be to calculate the payoff of the option at the time of expiration. And then we're going to use that payoff to calculate the values of the options at previous points in time. And we're going to keep doing that all the way until we get to the option that we're trying to value today. And that is going to be called backward induction. So here we have a little model that basically describes, this is a one-step binomial model. So we have our probability that the stock will rise. Probability that it will fall is going to be 1 minus p. And so this will bring us to our stock price of the future. And then we're going to use the stock price to calculate the payoff of the option. And then we're going to use the payoff of the option to calculate the payoff of the option today. And then the same thing happens if the stock moves down. So let's take a look at a generalized model. Okay, so this is basically a general version with t equal 4, so 4 steps. These are the equations that result based on the assumptions of the Cox-Ross-Rubenstein model. If you notice, u and v are actually multiplicative inverses. So anytime that they multiply each other, it's going to be 1. So that is the reason why you see here, for each row of stock prices, it's all the same. So if we have, for example, our initial stock price, and we move up and down, we end up at the same place if we went from our initial stock price down and up. So we have our initial stock price for all of these, and then our S1 is going to be equal to S3, and the same on the way down. And this is a pattern that will continue all the way until our last step. This is going to be our probability equation, and this will dictate the probability that the stock will move up, and then 1 minus p will be the probability that it moves down. This is going to be this function, this equation right here will allow us to price the options of not the final nodes, but the nodes prior to that. So we're going to use this VT equation to calculate the value of the option at t equals 3, t equals 2, t equals 1, and t equals 0. So for t equals 4, we could just use the payoff equation that we're all so familiar with. And just to clarify, we have VU is going to be the value of the option at the t plus 1 upper node, and then VD is going to be the value of the option at the t plus 1 lower node. So this is why this VU and VD are using the prices of the options at in the future to price the option at an earlier time. So that's basically the blueprint of the model. Now let's take a look at an example. So here we have our characteristics of the option. We have our the price. The initial price is going to be 25. Our strike price is 21. We have a volatility of 15%, risk-free rate of 7%, a delta T of 1, and it's a call option. So we're going to start off with our initial price, and then we're going to use our up factor and our probability to determine the price that it is at the t plus 1 node, which will be S1. And so we're going to do the same thing for the lower node of t equal 1, and we're going to continue this process all the way until t equals 4. Once we get to our final nodes, we're going to calculate our payoff. So our payoffs are going to be 20.55 for S4, and then for this S4 right here, our payoff is going to be 8.75, and then we're going to use the function that was on the previous slide to calculate the payoff of the option at t equals 3. Excuse me, the value of the option at t equals 3. And then we're going to use this backward induction process to go all the way back to our value of the option today, and end up with 7.39. So that is pretty much the binomial tree model. This is my example, and that pretty much got to us. We're going to move on to Monte Carlo simulation. So take it away, Andrea.
Hi again, Professor Hahn. I'm just going to quickly go through some of the initial research I did on the Monte Carlo simulation, why we use new finance, and then go through my code a little bit, my Python code, and some results. So this statement basically says that So one of the really good examples of understanding what a Monte Carlo simulation is determining pi, and that is by taking a circle and actually superficially putting it on top of a square, and then pretend you were figuratively doing something like throwing a bunch of darts and using some parameters to see, okay, are my darts inside the circle or outside the circle? How many darts are falling inside? And then taking an average of the many times you've thrown these darts and look at the convergence to determine the area within inside of the circle once you basically filled it up with all these darts. And if you see the next slide, this shows you the circle, it goes on the square. The next slide. And then here you see by choosing random points within the square, we're able to calculate whether or not each point is within the circle or not. And we can consider the analogy of throwing darts randomly at a dartboard, as I said. And then, of course, I'm sure you know the math behind the area and length of a circle and a square. So therefore, we can come up with a ratio by experimentation. We can use it to derive the value for pi. And the method requires that we generate pairs of random numbers. So this goes back to when I was saying finding out where the figurative darts are being thrown or where your simulation is happening. You would need to have a random number generator to determine, to make sure that these numbers have a uniform distribution. And that there's an equal chance of hitting any point on the dartboard. That is to say, you're not just going all over some white plane or some geometric plane, but you're staying within the square that the circle lies within as well. And for my research, I chose the Gaussian distribution method, which was just one of the more popular random generators that I found online, and also very simple to use with NumPy in Python. So why do we use this in stocks? So in finance, the underlying random variables, such as an underlying stock price, which is what we had, are usually assumed to follow a path that is a function of a Brownian motion. So a Brownian motion, as I understand it, is actually a random walk, actually similar to what Pete was saying with the binary tree. Is that what Pete was with the binary tree, the random walk?
Yeah.
So it does the same thing. It kind of gives you a geometric walk, a spread along a path, say some time to expiration, and it sets out. I'm not sure exactly how it does it, but it sets out some kind of stochastic random process to give you an average number after you give some parameters like an expected rate of return. And then I have the formula as follows. And I actually use the Black-Scholes model as our expected rate of return to use in our simulation path, along with the Gaussian random number generator to run the simulation. So next slide, I'll show you. So you'll see in my Python code professor that instead of actually using mu and some expected rate of return, within the code for the prices, you'll see that for each day, I've actually calculated the rate of return using the Black-Scholes model instead of the Brownian motion. I do want to go in and use the Brownian motion as well and do a comparison to see what it would look like. So what else in the Python code can I tell you? We use the stock price for today, for April 24th, and went out 3 days as we requested. And our number of simulations was 4, also as we requested. And that, interestingly enough, next slide, when we look at something like Apple and Google, I did note that, as the research states also, when you have a very low number of trials, you actually don't have, you have a much higher spread of where the price might be. So I would say this is probably less useful than if you have something like 1,000 or 1,001 trials where you have a convergence to one price like you had in your sample code. And so for Intel and Oracle, we see the same thing. We have our 4 trials here, and the stock starts for Intel at 23. It can go anywhere from 21 to 20, a little under, between 25 and 25.5 in 3 days. And for Oracle, it can go from 31 to a 33.6. And again, if we had, perhaps I can also show this in the final project, if I went out for 1,000 steps, we'd have, due to the algorithm itself, we have a convergence to the middle. So we'd have probably a more valid idea of what the prices would look like. Microsoft and Yahoo. All right, so that was Monte Carlo simulation, and I will also make my charts much prettier, Professor Hahn, and play around with the legend and the trial legend as well, to make it nice and pretty, like your MATLAB fun. So now I'm just going to briefly go through part 4, which are just some notes on algorithmic trading. What is it? So there's a lot of text here, but basically it's using mathematical models to trade instead of having a trader go out and buy stocks. Why do we use it? So it's fast. Algorithmic trading allows for you to build a model efficiently. It allows you to test models, and it allows you to allow for rule-based strategies that give you speeds not possible by having a trader go out to the market and look for a particular stock. And when we look at big data analytics, that a rule-based algorithm could be predictive, it could be prescriptive, and it could be descriptive. So that's to say you can take a lot of historical figures that you wouldn't be able to do the way traders do. And I'm sure you know with prescriptive and predictive, what we mean is running something like a neural network to look at trends and patterns in the data, and then have the network itself give you new analysis on what the stock might look like, 3 years out. And then minimal transaction cost. So I think about this analogy would be parallel processing versus one big server. So a lot of exchanges have volume sets, limits set on trading volume. But with models, you can actually go out and say, we're going to chunk it up into bits of stocks and have the different models running on different exchanges at different times, so you're never actually really hitting your ceiling for how much volume you can trade in one day or in an hour and in a minute. And that could be good or bad. Precision. So algorithms allow buy-side firms to fine-tune multiple parameters, start time, end time, aggressiveness, and I mean, this is self-explanatory. You can go in and tweak each indicator and tweak each parameter as you like and fine-tune it where you wouldn't really be able to do that with a trader. And simulations, so models can be run through various simulations and perspectives before they're executed. That's awesome. So some pros and cons. The pros are very similar to the last slide, except you remove the emotion factor. So I thought this was really interesting, especially with times of high volatility. A model is not going to get greedy or scared or nervous, and so that takes out the human error effect. And back testing, you can apply trading rules to historical data. Consistency, your model doesn't do one thing one day and do one thing the next if you give it the same parameters. It will always process the same information according to the variables that you give it. Improved order entry speed, so orders are generated, the minute trade criteria is met. So you don't have someone looking at material or looking at information, processing it, pricing, seeing what the pricing would look like, and then saying if it's good to go or not. The model automatically does it. And diversification. So of course you have the ability with increasing speed to go out onto different exchanges and do a lot more in less time. And the cons are clear. I mean, you have mechanical failure that can cause big losses. Monitoring, so you don't really need a trader to go out and do any buy or sell, but you do need to make sure the models are doing what they're supposed to be doing, and that means you need people to develop the models, and then the people to watch them also actually need to know what's supposed to be.
I think it's worth mentioning actually an example that we saw yesterday in the market, that there was an AP's Twitter that was hacked, saying that there were 2 explosions at the White House, and this news was immediately read by these algorithmic trading software, and we saw that the Dow immediately dropped 142 points, and then jumped back up once these rumors were cleared and they were debunked. And so this is an example of a con that sometimes you have very fragile conditions in the market, and one little knock on these conditions will cause a lot of trouble. So that's just another example of a con.
Thank you. That is okay. Yep, that is very true. And so, additionally, with that, you have one other con that speaks to that as well as the median, over optimization. So it's related to back testing as well, and that has to do with, you can remove the emotion factor, but the people who make the models also have an emotion factor, and so you might find someone trying to optimize a model way too much because they want to seek higher gains, and that could cause either an increase in mechanical failure because you're overloading the model with too many parameters, or you're tweaking it too many times, or it could just lead to bad results because it's not, we're not ready right now for certain sophistication in the mathematical models out there that are ready for trading. And that brings me to my next slide. Yes, so the future of algorithmic trading. So Professor Hahn, it's important to note that I did read some of the pieces of the papers, but this piece is actually, and I'll send you a YouTube link of a algorithmic trader himself in the field talking about what he thought was the future, and a couple of other pieces that I read. So right now, black box trading, algorithmic trading is mostly prevalent in cash equities markets, but what we should be seeing in the future are algorithmic trading in multi-currency markets for futures and options, black box hedging. That's done now at places like Renaissance Technologies, or also known as Rentech, but it's still very new. There's also a lot of talk of people going into the fixed income market and debt securities with algorithmic trading. And then last but not least is the idea of actually having this exchange-based, high-speed, single throughput, multi-asset system running all on mathematical models. So it'd be interesting to see that happen. And then an example for that would be an equity derivative and delta hedge, and the cash position is the underlying on a single platform with low latency. So I just see that being a big data problem also. But, and then you asked us to find out what it would take to be an algorithmic trader. So I went and I tried to find a job description from a really, really important bank, and for a lead algorithmic trader. And so this is from RBC. And a couple of things I know, but it is important to note that they want Java or C#, C-Pound, but I guess C++ might be better. They want you to be able to understand a number of non-software things like agile development methodologies, which is system development, and allowing for testing feedback loops. They also want you to be able to do a lot of GUI development, which I thought was interesting, user interface development. And surprisingly enough, there's not a lot of business terms here. It's all systems development, coding, and software skills. So you probably wanted to let us know that this is what we're going to have to learn if we want to be algorithmic traders, and that it's going to be started with your class. All right, that's it for me, Professor Hahn. Thank you very much, and we will be sending you our final project soon.